Hello Advanced Physics students, this is Dr. Burns here, and this is a video on lesson 8.1. And in this lesson we're going to identify key properties of a new force, which we're going to call the electrostatic force. And then we're going to calculate the magnitude of this force between two charged particles. Now, I want to go into a little bit of history about this electrostatic force. So this, actually the ancient Greeks knew a little bit about this force because when they rubbed amber, which is this substance right here, it's basically petrified sap from a pine tree. So if you rub this with a cloth or with wool, you can actually create a force that attracts light objects to this amber. And that's all that the Greeks knew about it, and they didn't really go into asking themselves, well, why does this happen? They just knew that it did happen, and they said, oh, well, that's that. It wasn't until the 16th century that people in the Renaissance started to read about what the ancient Greeks learned and knew, and they said, well, we should check this force out and see what we can learn about it. And so throughout the 16th, 17th, and 18th centuries, we get these scientists that do experiments that actually develop our understanding of what the electrostatic force is, what we now call the electrostatic force. And a few of these people of note is this first guy. He was a Dutch scientist named Van Musschenbroek. And his big contribution to our understanding was that he created this device called the Leyden jar, which other scientists throughout the next 200 years actually used to understand electricity. So without his device, we wouldn't actually, none of these other people who came later on would actually have any understanding of what electricity is all about. Another person that made a big significant contribution was this guy named Alessandro Volta. You might recognize that name Volta. If you take off the A, it gives us our units with which we measure the what we call electric potential of batteries. And he actually was the inventor of the very first battery. And you actually see his battery behind him. And then there was another guy, his name was Henry Cavendish, and he actually did an experiment to actually figure out, among other things, exactly, well, let's put it this way. You're going to actually find out what he discovered on the next page, in a couple of slides here. But he made a huge contribution, actually, to electricity. And these aren't the only three scientists who made big contributions. There are others, but these are the three that I just decided to throw out there. Okay, so what have we learned, and what did these people in the Renaissance learn about this electrostatic force? First of all, we've learned that objects can carry a positive or negative charge. So there are two different types of charges we figured out, and what we learned is that when something has a positive charge, it's attracted to something that has a negative charge. And likewise, when two positive charges are placed near one another, they actually repel one another. They push each other away. They don't like each other. And the same goes with two negative charges. You put them next to one another, and they don't like each other. They want to go away from one another. So opposite charges attract one another, like charges repel. Now, even the people in the Renaissance really couldn't have a true understanding of what's going on with charge until we had our modern understanding of the atom, which didn't come until the early 20th century. And what we now know is that these parts of an atom called protons are actually responsible for carrying positive charge. They form the nucleus of an atom, and I'll show you that in a slide here. And then negative charge carriers are called electrons. And each of these has a unit amount of charge. In physics, we measure charge in terms of coulombs, and I'll tell you why that is later on. But in terms of these units, an electron has a charge of negative 1.6 times 10 to the negative 19 coulombs, and a proton has a positive charge of the same amount. Now, you might be wondering, why in the world do electrons and protons have such a small amount of this charge called a coulomb? Yeah, well, it turns out it's because we didn't have a good understanding of what exactly charge carriers were. So we arbitrarily picked this some amount of charge that equals a coulomb, and it turns out that when we had a better understanding of what electrons and protons were, it turns out they carried actually very, very little of it. So it would have been nice to actually pick different units, but the people who picked the units didn't actually know about protons and electrons, so kind of stuck there. The other big thing that you need to understand is that neutral objects have an equal number of positive and negative charge carriers. It's not that neutral objects have zero charge, it's just that they have an equal number of positive and negative charges. Now, the other thing I want to talk to you about is this thing called Coulombs Law. And this was another famous person who lived in the, it looks like the 18th century here. His name is Charles Augustin de Coulomb. And he discovered that the amount of force that two charges exert on one another, so let's say you have a charge Q1 and a charge Q2. If they're separated by a distance r, then what Coulomb discovered is that the amount of force that they exert on one another is proportional to the product of the two charges, so Q1 times Q2, and it's inversely proportional to the square of the distance. So that's what Coulomb discovered. Then it actually took some time later until another guy that I mentioned, Cavendish, came along. He was actually the one that was able to figure out what this constant K is. And he measured that with a very clever experiment and discovered that it's 8.99 times 10 to the 9. And that is if you have your charges in coulombs and you have your distance in meters. So Coulomb and Cavendish actually came together. Well, they didn't come together, but they independently figured out different parts of how force works with electricity. And this is what we call the electrostatic force. And this is, and we call this formula Coulombs law. All right, so let me give you an example of how to apply Coulombs law. First of all, let's say that we have a dust particle, and it has a charge of plus 0.5 nanocoulombs. So let's draw that charge, 0.5 nanocoulombs. And it's located at a distance of 3.5 centimeters away from another dust particle whose charge is negative 1.0 nanocoulombs. All right, so there's our picture there. And then the question asks, how much electrostatic force does each dust particle exert on the other? So this particle is exerting a force on this dust particle and vice versa. So the question is, are these charges being attracted or repelled? I can ask myself, well, let's see, do they have opposite charges? Yep, they have opposite charges, so I know that these two charges are going to attract one another. So the blue dust particle is going to be pulled toward the left, and the red particle is going to be pulled toward the right, and they're going to come together with the same amount of force, and we can use Coulomb's law to calculate what that amount of force is. Okay, so I'm going to write down Coulomb's law. F equals K times Q1 times Q2 over R squared. Now, I have to use charge in terms of coulombs for Q1 and Q2, and I have to use meters for R. So Looks like I have to do some conversions here first because I have charges in nanocoulombs, and I need those in coulombs, and I have a distance in centimeters, and I need that in meters. So let's convert. Let's do a conversion here. So I have 0.5 nanocoulombs, and I'm going to divide that by the number 1. And then what do I put on top and what do I put on bottom? Well, I want to cancel out nanocoulombs. So those have to go on bottom here. And then that means that coulombs have to go on top. I know that there is 10 to the negative 9 coulombs in 1 nanocoulomb. So I'm going to put 10 to the negative 9 coulombs equals 1 nanocoulomb. And now I just have to multiply across for the numerators and multiply across in the denominators. And when I do that, I get 5 times 10 to the negative 10 coulombs. Okay, I can do a similar process for Q2 because I have to convert that to coulombs. And what I get for that one is positive 1 times 10 to the negative 9 coulombs. The distance I have to convert to meters, and hopefully you know that conversion a little bit more readily than the charges, so I just went ahead and did that conversion, 0.035 meters. Okay, so now that I have all of these converted to their correct units, coulombs and meters, I can go ahead and plug those into Coulombs law. I'm going to have to do that on another slide since I've run out of room here. So let's rewrite that law. And I'm going to have a big, huge fraction bar here. So this is Coulomb's constant, 8.99 times 10 to the 9. Let's enter that first charge, 5 times 10 to the negative 10. And one thing that you may notice is that I decided to leave out the negative sign here. The reason I chose to do that is because we're so used to thinking of force as a negative force as being to the left and a positive force as being to the right. But that's not how Coulomb's law works. So to avoid confusion, what I'm going to do is I'm always going to make these charges a positive number, which will give us the magnitude of this force. And then we're just going to figure out whether or not charges are attracted or repelled to figure out the direction of that force. So let's strip out all of the signs from each of these charges when we're calculating with Coulomb's law here. Okay, so I'm going to leave out the positive sign for the second charge, and I get 1 times 10 to the negative 9. And then I need to divide that by r squared, 0.035 squared. Okay, when I evaluate all of this, what I get in the numerator is 45 times 10 to the negative 10. And what I get in the denominator is 1.2 times 10 to the negative 3. And the final number I get is 3.8 times 10 to the negative 6 newtons. Okay. Now, if for some reason you forgot and you left the negative sign in here, well, you would end up with a negative sign right here. Okay. If you end up with a negative sign right here for Coulomb's law, I want you to take it out. Okay. I know that I may have taught this in class differently depending on when you're listening to this, but let's leave the negative sign out. It just seems like it's confusing people more than it's helping them. So what I'm going to do instead is I'm going to come back to my diagram. So I'll put the diagram back down here. And I have to remember that, oh yeah, this charge is being pulled to the left by 3.8 times 10 to the negative 6 newtons. And this charge is being pulled to the right by the same amount of force, 3.8 times 10 to the negative 6 newtons. Both of these forces are going to have the same magnitude. Newton's third law says they have to have the same magnitude because they are an action-reaction pair. It's just that one of them is going to be pointing to the left and the other one is going to have to point to the right. Okay, so that was the first example. I actually want to do a second example here for you because the level 2 problems get more complicated than this. So let me give you another example. So let's say we start off with those same two charges, but this time I'm going to add a new level of complexity by putting a third charge in here in line with those other two, but at a distance of 5.5 centimeters away, and we're going to give it a charge of positive 2 nanocoulombs. And I am going to ask myself, what is the net force? Oh, I put net charge there. Whoops. That should be force. Yikes, let's change that. What's the net force? What is the net force acting on the 1.0 nanocoulomb charge? Okay, now, in order to figure this out, what I have to do is I have to think about just two charges at a time, because Coulomb's law only works with two charges at a time. The charge that I'm concerned about, the charge that I want to think about, is this one right here, because it's asking me, the question's asking me, what's the net force on this charge? So I would actually put a star above that one to remind myself, that's the one that I'm concerned about. That's the one I'm calculating forces on. Now, I want to think about that charge and each of the other charges one at a time, because Coulomb's law really only works for two charges at a time. So I could draw an imaginary box around these two charges right here. So let me draw that. Let me draw that imaginary box. Let me give it a color purple. All right. So I'm going to draw an imaginary box around these two. Let's make it a little bigger so I can include the distance there. And I'm going to think only about these two charges. Okay, the one that I'm concerned about and one of the other charges acting on it. And I'm going to completely ignore any of the other charges that are in the picture. What I can do now with just looking at these two charges is that I can calculate the force between these two charges here. So I can calculate the amount of force that the red charge is acting with on the blue charge. So when I do that, that happens to be the same number that we had in example 1. After all, I started off with example 1. So you could actually use the same steps we used in example 1, and you're going to calculate the same amount of force, 3.8 times 10 to the negative 6 newtons. Okay. Now, once I've done that step, then I come over to the other two charges, these two, and now I think about those two and ignore the red charge. So now I think about these two charges, and now I have to apply Coulomb's law to these two charges. Now I'm going to just set that up for you, just so you can make sure that you understand how to do this. So I'm going to, whoops, I forgot to mention something. The arrow here, I just remembered, reminds me that these two charges are the same amount of charge, okay, which means that these two charges are going to repel one another. So this blue charge wants to move away from the orange charge, so the orange charge will push the blue charge toward the left. It'll push it away. So both of these forces are acting in the same direction. Question is, what's the magnitude? In order to figure out the magnitude, I have to apply Coulomb's law. And this might be what it looks like. So F2 equals, there's Coulomb's constant. The first charge is going to be our blue one, so let's enter that charge. The second charge is going to be the orange one now. And then we're going to divide that by now 0.055 squared, because that's the distance between these two charges. Okay. When I do that and I evaluate this big fraction, I'm going to have to erase mine because I don't want to start a new slide just for this one number. So I'm going to actually erase all this. Don't do this on your paper. But that comes out to 6.0 times 10 to the negative 6 newtons. Okay. There are two forces acting on this charge, and I'm being asked what is the net force, okay? These two forces are pointing in the same direction, which means I need to add them together. So I'm going to add 3.8 and 6.0, and I am going to get a net force of 9.8 times 10 to the negative 6 newtons. And my diagram tells me that that force is pointing toward the left. Okay. Now, one thing you might be asking yourself real quick is that what if this arrow was pointing toward the right? Well, that means I would have to do subtraction, and then I would give this a negative number, give that a positive number, because this is pointing toward the left, that would be pointing toward the right, and then I would get my net force by using subtraction. Okay, well, hopefully that will set you up for success on the 8.1 homework. I hope you have success with it, and I'll look forward to talking to you soon. Bye.